Hi boys and girls, this is lecture 3.8 in Unit 3, the topic Extrema on an Interval. This is a curve sketching topic, which means it will explain how the derivative can be used to describe certain features on a curve. Starting with extrema. There are two types of extrema, a minimum and a maximum. A value is a minimum of a function on an interval if it's the lowest value in that interval, and a value is a maximum of a function on an interval if it's the highest value in that interval. The minimum and maximum values on an interval are called the extreme values or extrema of a function on an interval. The extreme value theorem states that if the function is continuous on a closed interval, AB, then the function will have both a minimum and a maximum value on that interval. If the function is continuous, there will be a high point and a low point on the curve in that specific closed interval. Let's see how this works. When graphing curves such as this one, you have probably used the max or min function on your graphing calculator to determine max and minimum values of a function. However, we're going to learn to use calculus to get that information. Here is a series of questions we're going to go through in order to help increase our understanding of this topic. First of all, does every curve have a max or min value? This is a great curve to look at to answer this question. There is no closed interval here, and the function is tending toward positive infinity and negative infinity at its end behaviors. And because of that, there is no absolute max or min value on this curve. We could say that in this region there is a local max, or in this region there is a local min, or we could narrow it down to a closed interval. What if I decided to look at the region just between -1 and 2? And I said on the closed interval -1 to 2 now, is there a max or min value? Now we can definitely say, yes, there is. This is no longer a local max, it's the absolute max on this interval, and of course this is the absolute min on this interval. The second question says, does every curve have a max or min value on a closed interval? And that answer is yes, if the function is continuous. Let's look over here. What if I narrowed down the region that we're looking at here, say between -1 and 4? And in this case, I could say, well, I've narrowed it down to a closed interval, and the extreme value theorem says that there's always going to be a max or min value. But notice on this graph, in this region, there isn't a max or min value because there's an asymptote there. The extreme value theorem says that it applies when the function is continuous. So we're only guaranteed a max or min value on a closed interval if we know that the function is continuous. You can see how this breaking continuity on our interval meant that we did not have a max or min value there. What is the slope at these extreme values? Well, let's go back and look at this max and min value. You can see that the slopes are positive on this curve. There's a moment at which it's at the maximum value where the slope becomes 0, and then the slopes are negative. Of course, as it reaches this minimum value, the slope becomes 0 again and then becomes positive. So what we find is at these max and min values, the slope is 0. Now you can see how the derivative might help us find these max or min values, because isn't the derivative a slope machine? Couldn't we use a slope function to determine points at which the slopes are 0? The next questions: what conditions might prevent a max or min value from occurring on a closed interval? Well, we discussed that before. That's over here where we have a break in continuity. That will prevent you from having a max or min value, and in this case, because of the asymptote that occurs within that interval. Can a max or min value occur at a place where the function is not differentiable? That brings us to this graph. This function is continuous all the way through, but we do have a point at which a derivative does not exist. However, there is still a minimum value here. This function is defined at 0, 0, and of course that's the lowest function value in the interval. So what we find is that a max or min value could occur at a place where the slope is not defined, where the slope is 0, or where the slope is not defined. We could possibly find a max or min value. Then the last question sort of ties it all together. What must be true, therefore, about the places on a graph where max and min values occur? First of all, we need to have a place where the function is continuous. There can't be a break there. And in both of these cases, continuity is in place, even though this is not differentiable. We also need the slope to be either 0 there, or for the slope to be undefined there. Those are the two slopes which would indicate that we might have a max or min value. Well, we've learned a lot from this list of questions. Let's put all of this knowledge into practice. Definition of a critical number. Let f, our function, be defined at c, some point in the interval. If f prime of c is equal to 0, meaning if the derivative at c is 0, or if f is not differentiable at c, meaning perhaps the derivative doesn't exist at c, then c is a critical number of f, our function. Now we're giving a name to the places on the curve where the derivative would be 0 or the derivative would not exist. Those will be critical numbers of our function. It looks like there are two such places on this graph. We have here a spot at which it looks like the slope of the tangent line would be 0, a place where the derivative would be 0. And it looks like here we have a place where the derivative would be undefined. Yes, the function is continuous here. Yes, it is defined here, but it's not differentiable here. We wouldn't be able to find a derivative. Yet, that doesn't prevent this from being a minimum value, a local minimum value on this section of the curve. And of course, where we found the slope to be 0, we have a local maximum value. What we find is that relative extrema occur only at critical numbers. If f, our function, has a relative max or a relative min at a specific value, then that number is a critical number of f. Any extrema that you see on a curve must occur at a critical number, a place where the slope is 0 or a place where the slope is undefined. Here we have guidelines for finding extrema on a closed interval. First, find the critical numbers of the function in your interval. That means we'll take the derivative of the function, set it equal to 0, and also see where the derivative is undefined. The numbers that are generated there will be our critical numbers. Then we'll evaluate our function at each critical number. So the numbers we found which have a slope of 0 or which have an undefined slope, we will plug those back into the original function to see what the y values are. Then we will evaluate the function at each endpoint of the interval. It could be that an endpoint generates a max or min value. The least of the values that we find will be the minimum. The greatest of the values that we find will be the maximum. Now let's find the extrema of this function on the interval -1, 2. Notice I've set up a table. I'm ready for us to examine the values that we find. We're definitely going to want the function value at the endpoints of the interval -1 and 2, so I have added those to our table already. We're going to need the first derivative of this function in order to find our critical numbers. Therefore, f prime of x is equal to 12x cubed minus 12x squared. You can see that this derivative is not undefined anywhere, so let's find out where it's equal to 0. When I set the derivative equal to 0, I'm going to factor out the 12x squared, and that's going to leave a factor of x minus 1. Each of these factors set equal to 0 will generate a critical number. X equals 0, and x minus 1 equals 0 gives me x equals 1. So two critical numbers we found by setting the first derivative equal to 0. These two numbers in conjunction with the endpoints gives us the list of values we need to examine to get max and min values on our interval. These are the only places where max or min values might occur. So we're also going to want the function value at 0 and the function value at 1. Remember that once you have the critical numbers, you go back to the original function to find the y values. So let's look at f of -1 first. Gives us a 3 plus 4, which is a 7. F of 0 gives us 0. F of 1 gives us 3 minus 4, which is -1. And F of 2 gives us 48 minus 32, which is 16. So we have 0, we have -1, and we have 16. The highest number is our max. In this case, the maximum value on this interval is 16, and it's occurring at 2. The lowest number that we have is one of our critical numbers, is occurring at one of our critical numbers, and that's -1. So our minimum value on this interval is -1, and it's occurring at 1. In our last example, we are once again asked to find the extrema of a function 2x minus 3x to the 2/3 on a closed interval -1, 3. We are definitely going to be interested in function values at the endpoints of the interval, so I have added those to the table. Now let's find our first derivative. F prime of x is equal to 2 minus 2x to the -1/3 power. If I rewrite this without a negative exponent, I'll have 2 minus 2 over the cubed root of x. We can clearly see that there is a place where the derivative is undefined, and that is at 0. And so this makes 0 a critical number of our function. Remember, we're looking for places where the first derivative is undefined or is equal to 0. So we'll need to add that to our table. We'll need to know the function value at 0. Notice that our graph verifies our analytic results. We can see the sharp turn in the graph at 0, indicating that even though it's defined there, even though it's continuous there, it's not differentiable there. That doesn't prevent it from being a possible max or min value, which is why it makes it a critical number. Now let's see where our first derivative is equal to 0. 0 equals 2 minus 2 over the cubed root of x. I'm going to add this term over to the left side of the equation. 2 over the cubed root of x is equal to 2. Cross multiplying at this point will give me 2 equals 2 cubed root of x. Then divide both sides by 2. 1 equals the cubed root of x. Cubing both sides gives me x is equal to 1. So at 1 we have a slope of 0. That makes 1 another critical number. We will need to look at the function value at 1. Notice once again, our graph verifies our analytic results. It does look as though there is a horizontal tangent here at 1. All right, now we need to see the function values at each of the numbers we found. At -1, when we plug that back into the original function, we get -2 minus 3, which is -5. At 0, we get a function value of 0. Notice that even though the derivative was undefined at 0, the function was not undefined. We did have a function value there. When we put 1 back into our original function, we get -1. And when we put 3 into the original function, we get 2 times 3 minus 3 times 3 to the 2/3 power. Now we are going to need to know what this is in comparison with our other values. So we should get a decimal approximation here for comparison purposes. It turns out that that's approximately -0.24. Now, look at the 4 values and let's see which was our lowest and highest values. The lowest value we see is -5. Therefore, the minimum value on our interval is -5, and it's occurring at one of our endpoints, -1. The highest value we see is 0. Therefore, the maximum value on our interval is 0, and it's occurring at one of our critical numbers, 0. And that's how you find the extrema of a function on a closed interval. That's it for today's lecture. Well, this is awkward, but at least those mice are providing a local maximum value on the curvature of the snake's back. That's something, right? God bless you, boys and girls.